welcome everyone. It seems like we are crowded today, so that's a good sign. I just wanted to mention that in 2 weeks there will be the deadline for the postdoc applications, and we are still looking for postdocs in astronomy. So if you know people that are working on black holes and might be interested, please encourage them to apply. We have until November 15th. And other than that, we'll introduce the speaker. Go ahead.
Right, so I'm delighted to welcome Janna Levin to give the Black Hole Initiative Colloquium today. Janna is a professor of physics and astronomy at Columbia University, and I think she's really a kindred spirit for us here at PHI because her undergraduate degree was from Barnard College, and she had a concentration in philosophy. So Janna's done wide-ranging research, including cosmology and black holes and gravitational waves. And she's even published several popular books on these topics, including a recent one on LIGO and the hunt for gravitational waves. And today she'll tell us about studying dynamics of black hole spacetimes with gravitational wave astronomy.
Thank you. Thanks, Jeff.
Right now.
I want you to clap after every sentence. It'll be like a State of the Union or something. I am giving 3 talks this week. So in an attempt to not repeat myself in 1 week, apparently I'm repeating myself from a couple of years ago by accident. I forgot I spoke on a similar topic at the CFA a couple of years ago. I don't know if many of you were there, but...
I remember it really well.
Yes, you and many people. I don't want you to think I'm not doing newer work, though, so I hope you'll come on Thursday at the CFA when I'll discuss some work with your own Dan Drazia, who's now a postdoc here, on slightly related but very different work in black hole theory. I'm going to do something, I don't know, completely different at the lunchtime one. I'll decide later. Maybe works in progress. But today I thought it would be worth discussing the orbital dynamics of black holes in some detail because we've had this remarkable year. I mean, something incredible happened in February was the announcement from LIGO of the first direct detection of gravitational waves. Obviously, you all know that. And there was also the announcement of another detection on Boxing Day and possibly a third little bump in the data. So it's all black holes all the time for LIGO right now, which is pretty amazing. I did. You know, the book was printed for Ray and for Kip on September 14th, by coincidence. And because I'm not in the collaboration, they didn't tell me. They told me a couple of months into it. Basically when they were sure and Ray couldn't stand it anymore. Kip didn't even tell his wife, so he could have gone forever, totally poker-faced. But yes, it was crazy because the opening of the book is almost exactly what happens in the detection. But, you know, we all knew that, right? The only thing, the title Black Hole Blues was inspired by Ray Weiss because he said if we don't detect black holes, he said this in August, the whole thing's a failure. That's what he said, which I thought was a very strong statement. And all the people in the experiment, I don't know how many LIGO people are here, but many people told me not to expect a detection until 2018, 2019. Black holes maybe even later. So this really was an amazing thing that happened. This is a numerical simulation, very famous, I'm sure you've all seen it, that's been going around, of what the detection on September 14th actually recorded, and that was, this is drastically slowed down. These are 2 black holes, about 1.3 billion light years away, somewhere in the southern sky. We don't know where very well. One of the black holes is about 35 times the mass of the sun. These numbers have moved a little. The other was about 29 times the mass of the sun. What was caught by the detector was only the final 1/5 of a second. Incredibly brief. This is drastically slowed down so that we can actually see it. They're going incredibly quickly in their orbits. They're only a couple of 100 kilometers across. You're looking at the final few orbits really recorded, which is what's fascinating, though, is what this means is that when the original detectors were up at LIGO, very likely those same sources were emitting gravitational waves. I mean, it's extremely what we assume to be the case, maybe even for a billion years. And so those gravitational waves were washing over the first generation of LIGO machines, and they couldn't detect it, and they couldn't detect it until the final 1/5 of a second, partly because of the advanced machine, but also partly because I was got really loud, right? So here's what they recorded. So this is provided by LIGO. Okay, so that's Hanford. So these are the 2 different events. And we can't really hear the low frequencies, so they're going to increase the pitch. It's a little friendlier to the human ear. So all that's going on. If you ever do this for a public audience, they just think this is hysterical. That black holes sound so wimpy, they just think it's absolutely hysterical. That lead-up time is just outside the human auditory range for most people for low frequencies. So we can't hear it, so you increase it in pitch, and still it's slowed down. That's not a fifth of a second, that was longer. Okay, so why is this interesting in terms of what I want to talk about today, which is orbital dynamics of black holes? Because we only heard 1/5 of a second, it really was the final few orbits. By then, it's going to be quasi-circular. So even if the orbits start out more interesting, they're going to circularize because they're losing angular momentum to the gravitational wave. So the final orbits, for sure, we expect to be pretty plain. Now, what if we can dig out into the data earlier? What if we can hear 15 minutes? What if we can hear longer? And so as we get better at doing gravitational wave astronomy, the aspiration is that maybe we'll be able to probe more interesting depths than just these sort of final quasi-circular throws. So what do we expect for the orbital dynamics? Well, we know if this was supposed to be Mercury, but the astronomers in here probably recognize that as a different planet. Any astronomers in here who are willing to shout out what planet it is? It's Mars. I think it's Mars. I don't know. I just took it off Google, you know. What is it? I know, it's a walnut, and I'm pretending it's Mars. So what do we expect? You know, from Kepler, pure Newtonian physics, we expect that circular orbits give way to perfectly closed ellipses. This is the magic of Kepler's laws, is that in Newtonian physics, the orbits are perfectly closed ellipses. It's a wonderful thing. Now, we know that that's not true in relativity. As we go from Newtonian physics to even the smallest relativistic corrections, we see precessing ellipses. There is no longer a closed ellipse solution in relativity. It does not exist. Anytime you have an elliptical orbit, the precession famously, the perihelion famously precesses. In the case of Mercury, this was the one fact that did not align with Newtonian physics. It was hardly the motivating factor for general relativity, but it was the first thing Einstein checked when he wrote down the full theory of relativity. He checked that he could correctly account for the precession of the perihelion of Mercury, which is 43 seconds of arc per century. Mercury's orbit is about 88 days, something like that. So per orbit, it's absolutely tiny. Okay, to accumulate 43 seconds of arc over an entire century, it's something like 10 to the minus 7 seconds of arc per orbit. It's really tiny. But he could correctly account for this, and he said, you know, of course, he had heart palpitations, he said. For days, he was so excited. Okay, so maybe this is what we expect for black holes, that we go from circular orbits to precessing ellipses. And as you get more and more eccentric, they're just more and more eccentric precessing ellipses, and eventually they become unbound. Okay, this is sort of what you expect for the solar system. In the strong field regime, or in black hole dynamics, that is not what happens, actually, interestingly enough, and this is what I want to talk about today. This is just a sort of randomly selected black hole orbit of a test particle around a spinning black hole, and that test particle is not only showing fully three-dimensional motion, it no longer lies in a plane, but it's showing some pretty peculiar orbits here. Okay, so it used to be that people just had no idea how to classify the orbits whatsoever. If I made a tiny change in initial parameters, it wasn't formally chaotic, but I just didn't know what the orbits would look like at all. It had no predictive power. Yes?
Dimensions there?
Okay, you mean how strong field? Very. So near where you're seeing a bound unstable orbit. So that means, you know, very inner regime. It depends specifically on the spin of the black hole, but for a short shell black hole, I mean, you're in 10 and under, you know. So it's a very strong field. But it doesn't mean that the apastron has to be in that close, just that periastron has to be in that close. So apastron could be extremely far away, highly elliptical. That doesn't really matter. Okay, so we have a test particle. These are integrable. We know how to find the geodesics for test particles. By integrable, I mean we know we have enough constants of motion. It's not formally a chaotic system, but it does resist organization. But if both particles spin, we actually do have formal chaotic solutions. And I'm turning off gravitational radiation right now, just for clarity. I'll turn it back on later. You can't really talk about dynamical systems with dissipation very easily. It's natural to talk about them as the gravitational radiation was just turned off, and then we can turn it back on again and ask what the observable consequences are. I'm going for about half an hour, is that right? Okay, you guys can just stop me if I keep going. So we try to figure out, how can we make a complete portrait of black hole dynamics if they look so crazy? And even though we can write down these analytic solutions, they're quite complicated. They depend on a lot of parameters. It just didn't seem to yield very well. But we knew something from Poincaré. Poincaré suggested that every dynamical system is reducible to periodic orbits. It's actually a very deep part of dynamical systems theory and chaos theory that this is the case. In Kepler's system, it's really just the ellipse. That is the only, topologically, the only periodic orbit in Kepler's system. But what do we have? What are the periodic orbits? And it's kind of strange to think about. I have a black hole sitting here spinning, something's orbiting around it. The ellipse is gone. We know that already in the solar system, that there's no more the closed ellipse doesn't even exist. So what's left? And what's left are these multi-leaf clovers. Okay, it turns out that there is an infinite set of periodic orbits that structures the entire dynamics. All eccentric orbits are these multi-leaf clovers. So we're going to spend some time looking at these. And so the anatomy is called zooms and whorls. This is various people blame each other for the name. Nobody will accept responsibility. But a zoom is the large, slightly more natural elliptical-looking part of the orbit, and a whorl is when it makes a nearly full circle at periaster, at point of closest approach. And we know because of perihelion precession that the leaves overshoot. Okay? But each time, just as it does with Mercury, it overshoots a little bit from its starting point. So we're going to use this thinking to find some pretty cool correspondences in the dynamics with number theory, which is one of these beautiful things that went from Poincaré through dynamics to the mathematics of number theory. So our question is, by how much does an orbit overshoot its starting point? And that's going to help us classify the orbits.
Are you only considering ones that close eventually?
I'm right now only considering perfectly periodic, and I'll argue that all orbits are arbitrarily close to some periodic orbit. And you can even say that about Mercury. It's like a really tight, multi-leaf clover.
So are you're not
thousands of leaves.
entirely in a plane?
I will get out of the plane
You'll get
soon.
out of it.
Yes. So right now, yes. Right now I'm looking at the Kerr equatorial for simplicity, and we'll be able to do this out of the plane.
Sorry, but you're not including gravitational waves, right? Because
I am not. I've
then
turned off
phase
gravitational
space is
waves.
like- So
Yeah.
what does it mean? So that means like you're in the test particle approximation?
Right now I'm in the test particle approximation, but we can do post-Newtonian with two black holes. We can do anything that has a Hamiltonian, basically. So any system for which you can write down a Hamiltonian, like a post-Newtonian approximation, or the full Kerr test particle spinning case.
But I mean, the full system, including the gravity waves, also has a Hamiltonian, but it's not periodic.
Oh,
It's
dissipative,
phase-based.
right, the Hamiltonian it's not really a Hamiltonian because it doesn't conserve energy, but yes,
No, it
there are
it absolutely
there are
conserves energy.
dissipative terms, absolutely, with the post-Newtonian gravitational radiation terms, but they can all be turned off because they're all half-order terms. So we have turned off gravitational radiation. So when you discuss dynamical systems, you have to turn off the dissipation first, and then we'll turn
General
it back on.
relativity is not a dissipative system. It has
She means the test particles.
Yeah,
Yeah, that's fine.
oh, but
It's
he
not
says that it's fine?
General relativity is not dissipative, that's for sure.
No, the gravitational radiation is dissipative for the test particle
Yeah, that I
motion. The
understand.
test particle motion decays. It does not have a constant energy. Okay, so every closed orbit, we're going to say corresponds to a rational number. So we're asking, by how much does this overshoot? And the precession is simply related to the frequency it goes around in phi over the frequency it goes around radially. That's not surprising. What's interesting is that we can break up this rational number, which describes this closed orbit in terms of the whorls, which are W's, zooms the number of leaves, and V the vertex of the leaf. So let me give you an example. This is one radial cycle of an orbit. It starts here at Bastian. It goes through one whorl, so W is 1. and then it goes to the first vertex in the pattern, so V is 1, but it's a 3-leaf clover ultimately, so Z is 3. Okay, it's a pretty simple scheme. And that is, of course, what omega phi over omega r must be to make this pattern. That's how much it must overshoot to make this perfectly closed periodic orbit. And in some sense, that's a cute nomenclature or numerology, but doesn't really do anything for you. But if we keep going, we start asking, is there a unique orbit that goes to the second vertex in the pattern? So it takes one whirl, so W is 1. It goes to the second vertex, so V is 2. And it has 3 leaves, so Z is 3. And that's also a 3-leaf clover. So what's the difference between these two, for instance? They're unique orbits. And what we find, which is quite amazing, I'm just doing this for a test particle around a short-shield black hole, but again, we can do this in basically any system. Famously, it's easy to do this in the short shield because we can write this down as test particle motion as though it's in a potential well when it's near the non-spinning black hole. So a particle moving around your classic non-spinning black hole has a stable orbit in the potential well where it just zooms around and flies. This perfectly circular stable orbit. Here's the unstable circular orbit that we mentioned earlier. And what we find is that as an energy level diagram, that the value of that number Q, that rational number Q, stacks in energy. Okay? So the lowest rational has the lowest energy in this picture, and the highest rational has the highest energy in this picture. So that's quite neat. It means the rationals stack in energy, and suddenly you're getting some traction with it. So we have a stable circular orbit, and in between we have an infinite spectrum of perfectly periodic orbits, each one corresponding to some value of that rational. So this is a neat orbit. This is called a homoclinic orbit because it's basically an infinite number of worlds. An orbit starts here at finite apastron, and it asymptotes to the top of this hill unstably, but it asymptotes to the top of this hill. It's called a homoclinic orbit, and it whirls an infinite number of times around there. So the top here is infinity, okay? Q is infinity, that rational is infinity. And at the bottom here, it's not 0, right? Because there's no ellipse. So what's the value at the bottom is something we'll ask also. So what we do is we build this kind of periodic table of black hole orbits. We have the ground state, which is just like as though we were building, it's not a perfect analogy, but as though we were building some kind of atomic states. The ground state, we have a stable circular orbit, and then as you go up, so energy is increasing top to bottom and left to right. So as you go up in energy, Q increases. So here, right above the stable circular orbit, is a rational of 1 1/3. And this actually is the bottom of what you can get. Like the lowest rational approaches 1 1/3. Okay, so it's basically an orbit that is not very eccentric, whirls once, overshoots, and goes to the first vertex. Here's 1 1/2. It's a 2-leaf clover with a whirl in between. Okay? Here's 1 2/3. It whirls and it skips, like we discussed with these people. Yes?
Maybe you'll get to this, but is there any simple expression for where the vertexes are in terms of distance from the black hole for a given set of numbers?
Oh, you mean where's apastron?
Basically, where do the lines cross each other? Essentially, the predictions of where those occur.
We really worked very hard on that point. Actually, it's not that easy to say, but the crossings tend to be pretty close to perihelion.
Sure.
So the more eccentric it gets, that doesn't seem to budge very much, is the point. So in other words, these are getting more and more eccentric, higher and higher energy in that potential picture, but that crossing stays pretty close to perihelion. The prediction for apastron, we can analytically write down what apastron is as a function of Q, actually. It's just not a very useful expression.
And the reason he's asking is because when a star gets disrupted, there are streams of gas left behind.
And when they cross, they brighten. Yeah. We have tried to use, I was working a little bit with Zoltan Hyman on something similar. Not necessarily star disruption, but if black holes get displaced and the disk starts to become eccentric in the orbits around the black hole, that there are also these crossings. So we haven't made much progress with that. But yes, could we tell the difference between a Newtonian orbit and a relativistic orbit just by looking at brightenings and things like that?
What are the axes in this periodic table?
So these are literally just spatial for each one. So X and Y as though it was a flat space-time, and energy is increasing from top to bottom. I haven't actually told you what the energy is yet, but we can look at it a different way. Let's see if it's on the next slide. Actually, let me do this first, and then I'll show you the energy level stackings. Okay, so we're arguing that absolutely all orbits, just as Poincaré said, are defined by this periodic set. So high Z orbits, that is, orbits with a lot of leaves, multi-leaf clovers with tons of leaves, can be seen as perturbations of low Z orbits, and this is really cute. So here's Q of 1 2/3, right? It comes in, it whirls, it goes out to the second vertex. You see it again because it's cute. And then it goes to the second vertex, and then it skips a vertex each time, eventually closing. Because that's Q is 1 2/3. But what about a Q, which is still a rational number, of 1 + 203/300? What does that mean? It means it whirls once, but each time it comes in, it skips 202 leaves and goes to the 203rd vertex in the pattern, and it does that each time around, and it has 300 leaves total. This number we know is very, very close to this number, so energy level-wise, these are very close to each other. It means a small perturbation in energy of this one results in this one, and that's exactly what it looks like. It looks like a small precession around this guy, right? Just like Mercury is a tight precession around the closed ellipse, these are tight precessions around lower order rationals. And that allows us to think about the entire space of possibilities just by looking at low order rationals, knowing that of course there's an infinite number of these arbitrarily close to this rational, but I don't have to individually study them or think about them. They're all perturbations of the nearest low-lying rational. Does that make sense? I think it's just a very sweet feature. And so, for instance, in this case, we know exactly how much this guy precesses around that guy. It's 1/100, which in degrees is 3.6 degrees. If I had chosen 1 + 2003/300, it would have been an even tighter precession. Okay, smaller number, smaller overshooting. And so this is great. Now we can think about the entire space of black hole dynamics in terms of these rationals. This is to Peter's question, showing energy on this side just evenly, totally normal scaling, and it shows the corresponding values of Q on this side, and this was for, I think, a highly spinning black hole, where Q starts large. So the interesting thing here, here's the spin of the black hole, 0.995. For this case, around the stable circular orbit, the first low order rational that we get is 1 1/3. It means there are no orbits that don't whirl, right? 0 orbits that don't whirl, because all orbits have a Q larger than at least 1 1/3. Okay, so that means that there's no precessing ellipses. And that's quite profound, I think. So as we look at Q, it starts to also get closer and closer as you go higher and higher up in this potential. But we're probably down here by the time we're looking for signals. So what was Mercury's Q? We just want to argue. So this value, this bottom value for Q, is dependent on the spin, and it's also dependent, obviously, on angular momentum. If you're very, very, very far out, your potential flattens quite a lot. It looks very different. So Q for Mercury is like 10 to the -7, and those simply don't exist in a strong field regime. There are no tightly precessing ellipses. So if you were imagining, when people are talking about doing matched filtering, to pull a gravitational wave signal out of the noise, let's say we want to go back to initial LIGO data and find the same black hole system that they found on September 14th. It's in the data, right? It's just incredibly quiet. Is there a way to pull that out of the data? And people sort of think, oh, well, what you do is you look for quasi-circular orbits, and eccentric ones are just nearby. It's not true. Eccentric ones are, in some sense, very nearby some other multi-leaf clover. They're not nearby a precessing ellipse. So the point is that all eccentric orbits in the strong field exhibit zoom and or whirl behavior. This is not strange behavior. This is the standard behavior around black holes in a strong field. I just want to emphasize, and we're going to get into all of this, that if you add the spin of the test particle in a black hole spacetime, that those systems do become formally chaotic. Actually, it's what we think happens is that this sort of set of periodic orbits that corresponds to the rational numbers gives way to a fractal set of periodic orbits, which you see happen a lot in chaotic systems, that the correspondences with the periodic orbits goes over something like a fractal set of irrationals, which we've seen in other systems, but we haven't completely proven the transition. But there are both Suzuki Yamada and my group has shown that there's definitive chaotic behavior in this system, and also in the post-Newtonian approximation to two comparable mass black holes, which is not a test particle limit, where both black holes spin. Once both black holes spin, you also get chaotic behavior. So you can turn off the spin coupling to reduce this to a non-chaotic system. Yes?
Sorry, so you may have said this and I missed it, but what about out of plane? Or maybe
I'm about to do out of plane, but that's a good point. So everything I've done is equatorial, and we know that when the black holes spin or the test particle spins, the equator is special. And so equatorial motion is special. You reduce a lot of the degrees of freedom. So when you're out of the plane, what happens is we know that there's spin precession as well as perihelion precession. The black hole's spins begin to rotate around the total angular momentum, and the whole orbital plane starts to move around.
But say there's no spin. Say the test particle is not spinning, but the black hole is spinning. Then do you expect somehow that it'll be in plane by the time we get around to seeing it, or should we?
Oh, that's an interesting question. Does spin precession dilute a lot due to gravitational radiation? Is that what you mean? Spin precession should not. But there are arguments about if they would align for other reasons. If their spins are aligned, then they're in the plane.
But like for example, just empirically, like in the galactic center, do we know that the orbits that we see from the SLA group or whatever, are they all in plane? I just don't know.
No, they're not.
I guess they're not, right?
They're not. I mean, they're not in the same plane as each other. Each one is in a plane of its own.
Yeah.
We don't see any precession of the plane, but they're not in deep enough to really be probing very relativistic spin precessions, and their spins aren't high enough because they're not compact objects. So because they're big fluffy stars, I just don't think you would see it. But what we can do here is we can define an orbital plane, the plane that follows, just like you would imagine, where the angular momentum is perpendicular to that plane, the angular momentum sweeps around, and the whole plane sweeps around. We found a way to do kind of a projection in the orbital plane that yields everything we would want. So let me show you this. Okay, so here, sorry, it went a little fast. Here's this orbit, which is very 3D. The orbital plane is precessing. When we project it into the orbital plane, again with gravitational radiation turned off, we get exactly the same taxonomy that we would have gotten for the equatorial orbits. So we simply add to this the knowledge of the other motion, and this orbit that looked completely hairy and crazy turns out to have this very beautiful interpretation in terms of a precession around the orbit. No, it's
or the
projection.
instantaneous orbit.
The instantaneous orbital plane. The equatorial plane gives you no joy. Looks a mess. So it has to be the instantaneous orbital plane, and we can even do this in curved systems where you just properly define your tangent space, your basis vectors, you just do it very carefully, and it works out perfectly.
And the coordinate itself, what are you? This is just R, Boyer-Lindquist R, or is it?
For Kerr, we use Boyer-Lindquist R, but we use a very funny coordinate system for the angles. This would basically be definitely not Boyer-Lindquist phi. So it's a phi defined in the projection of the orbital plane. We have to do a little bit of careful geometry to make sure we get the right phi. And then there's basically the angle of precession on top of that. But it's in some sense a simpler coordinate system than Boyer-Lindquist in that once the angle of is mostly constant of the precession, right? It just basically precesses around the total angular momentum. So this is where all the detail is. Okay, so again, we emphasize that all these orbits would precess as long as they have any eccentricity whatsoever, and the precession is extreme. This is something I did with Deirdre Schumacher and her student Healy, but we did this in full numerical relativity, so in this case, gravitational radiation is turned on. The problem with full numerical relativity is that you can't do that much in terms of strong distances. You can't use a grid where you have varied distances. That's very hard in numerical relativity. And you can't do that many orbits because it's so computationally expensive. So this is just the final few orbits of a system that we imposed some eccentricity on it. And you can see, details in the gravitational waves, and I'll argue that you can hear them. But this is just to show that it can survive the gravitational radiation back reaction. But probably what we would imagine is really in the early parts that the orbit would be eccentric, and in the final few orbits that by then we wouldn't really gamble on it retaining that imprint. So this is a simulation where I'm showing a heavier black hole, about 10 times the mass of this lighter black hole. I'm just painting their orbits again, helpfully. And it's a fully 3D orbit. And it's just interesting to think about what it would sound like. Notice it gets quieter when it points away, which is really cute. It gets louder when the whole plane comes back.
The gravitational waves.
Yeah, so this is literally what you could record with LIGO if you could get a minute. And it's not the same as the circular. So it's neat that you can hear these details. Unfortunately, all we ever get is the whoop, or at least 3 times all we've got is the whoop. But what if we got the final minute and it sounded like that? That would be pretty astounding. It's a way that you not only extract things like spin parameters, but you can really hear the precession. And if we don't have great amplitude extraction capability yet from the data, but so telling that it got quieter and louder is probably far, far, far off. But the neat thing is you still see that even with the gravitational radiation turned on and this thing getting closer and closer, and so it's not really perfectly periodic orbits anymore, but it's like you're moving through that. As the energy decreases, it's like you're moving through pages of those periodic tables, right? And you can even see clearly the multi-leaf clover behavior now that you know what you're looking for. So I think I'm at my half hour exactly. So I'm just going to give my take-home messages that generic orbits are processing multi-leaf clovers. There's no such thing as the processing ellipse of Mercury. Simple match filtering won't find them using standard templates because they are so different in some sense. They're not slightly variations of the circular orbit. This technically could be a way to search, to design an algorithm to search by moving through these periodic tables, because of course, I don't know if you've heard this, but match filtering is really burdensome computationally. It's so burdensome that we've never searched the past data for eccentric orbits. I mean, the first generation of data, the 7 runs or whatever it was, if initial LIGO has never been searched for eccentric orbits. It's pretty amazing. There could be detections in there. If LIGO detects misaligned spins, we might even see chaotic behavior, which I didn't really go into. Everything I showed you was either one body spinning and not the other, or some way of avoiding the chaotic behavior. The chaotic behavior is not going to be that disruptive. You're going to have a kind of hedged in space, maybe very unequal mass black holes, but not extreme mass ratios and large spins. So it's going to be a very narrow region where you see chaotic behavior. And when that does happen, there's probably some very deep number theory correspondence when you give over to the irrationals. And then just to give a plug for my talk on Thursday, I'm going to talk about something completely different. Work with Dan, as I said, where we talk about how to make an electronic circuit out of a black hole and a highly magnetized neutron star, and predictions for how that electronic circuit might create luminosities that we could hope to see for a multi-messenger signal. Thank you.
So with these kind of orbits, is there any way they could be imprinted on an astrophysical accretion disk?
Yeah, I mean,
like
that's
density
sort of
waves?
what Avi was mentioning. It could. And I started to do a project like that with Zoltan Hyman, who is a great physicist, but we just didn't finish it, But yes, it could be that in accretion disks, if there's any eccentricity in the orbits for whatever reason, there was a kick that the black hole received, so accretion disk gets kind of displaced, and that makes the orbits kind of eccentric. That there could be different patterns of crossings which lead to different brightnesses in the disk.
The simplest example would be the tidal disruption of the star, because then
Yeah.
the tail follows these orbits.
Yeah, that's a cool idea to look at that restricted case. Yeah. Yes.
What did you look at the massless particles like photons, and how do their orbits compare?
Yeah.
I mean, there is the bound photon orbit, but inside of it,
The photon doesn't have a stable circular orbit.
but there is a potential that describes it this much more.
Yeah, but it's inverted. It's like that.
Right.
So it has an unstable, but no stable. And so it does have, so I can answer it even, without having solved it. It does have a homoclinic orbit where it can asymptotically approach and whirl an infinite number of times, but it doesn't have anything else, because it needs the stable circular orbit to move above it to have an eccentric. So if you tried to give it any eccentricity, we know what happens. It falls in or it goes out. And that's the whole story.
That's also for care, not just visual.
Yes. Yeah. Until the photon develops a stable circular orbit, you don't see any other interesting dynamics. But it can do that in a binary black hole system. So we were looking at the orbits of the black holes. If I look instead at a photon around the orbiting black holes, then you can get funky orbits for the photon. And those are chaotic systems for sure, where you add a third particle as a test particle. So even if you look, there's a space-time, Majumdar-Papapetrou space-time, where two black holes are charged in such a way that it's a static space-time. So the electrostatic repulsion perfectly balances the gravitational. So they literally just sit there. It's a static space-time. And that, obviously what you can do when you can write down a metric is a lot, and you can prove that those have chaotic orbits. And fractal sets of both photons and regular matter. It's fractal sets of orbits. The orbits are fascinating. Yes. And again, there's a correspondence with your rational numbers. So that's really neat.
So
Yes.
you see that you will talk about the black hole and neutron star.
Yes.
From the orbit point of view,
Mm-hmm.
if the test particle is so cold,
Yeah.
finite values,
Mm.
tidal forces,
Yeah.
spin interaction.
Spin-spin interaction we can include, and that's when we start to lose for point particles, though. Spin-spin for point particles we can include either through Kerr with fully spinning test particle or through post-Newtonian terms. And you will lose one of the constants of motion, and some of this will begin to show chaotic behavior in a very, very thin region of parameter space. Extending the body is just very, very hard. I don't think there'd be much joy in doing it analytically. I think that's something we'd have to do numerically to get anything interesting. I've tried.
Searching the data is impossible.
For an extended body,
Yeah. It's small enough. Because
well, I guess what I would say is the tidal force, let me put it this way, actually. Maybe this is relevant. The tidal disruption of a neutron star is actually quite hard to do with the black hole. The black hole has to be small to tidally disrupt the neutron star. It has to be smaller than about 6 solar masses for a non-spinning black hole. And that's like saying, if I stand on a basketball, I notice the curvature more than if I stand on the Earth. So in some weird way, the smaller the black hole, the worse the tidal force is. And so a big black hole just swallows a neutron star complete. And so one of the reasons why we're moving into this regime is that the test particle motion actually is, there might be, problems with wobbling or pre-complete tidal disruption things, but basically if the black hole is 30 times the mass of the sun, it is a test particle, that neutron star. Even if it's 10 times the mass of the sun, it's pretty close to a test particle. And so one of the reasons we were so excited about this project was because in the absence of tidal disruption, since most black holes will probably not tidally disrupt their neutron star companions, this is a novel way to actually brighten those systems. So we might hope we could see them even if they don't tidally disrupt. And once you see them, then you reconstruct backwards on the orbits and things like that. Yes?
So as to the initial gravitational wave event from LIGO, do you think there's prospect with sort of, I guess, more guided searches looking for these sort of rose petal patterns to go back and say the week before or something. Is there hope to find some data signal?
So I don't think the machine was fully locked the week before. And they were doing a lot of tests. They were constantly interrupting the machine the week before. So you could ask of any of their engineering runs. That was the first science run. Are there any episodes of uninterrupted data that they could begin to scan? I mean, it's a great question. I think, I don't know if they're doing that or not, but you would sort of hope they would, but they might just feel that it's too low below the noise. And this is what they got. They did that in some sense. They had a huge SNR at the end, and they did that in some sense and dug into the noise going back as far as they could, and then I think that was that.
So is there anything you could learn better potentially by isolating this early time signal?
Well, what one hopes is that as LIGO improves, we'll hear longer wave chains. So I guess the answer is that we know that LIGO can't do better than they did because they had some hours of data and they only got a fifth of a second. So they must have tried to go as deep into that data for this back a few hours as they could have. So that's most likely the case. But yes, in the future, when the maybe a black hole will only be 900 megaparsecs away. And actually, that's still too far. Push it in, 500 megaparsecs away, and we'll hear, and it'll be bigger, and we'll hear a longer signal. So I think that's the hope. Yes.
So what struck me about your video with the sound in it was that orientation really mattered a lot for how loud it was. And I'm curious, is it possible for the merging system to be loudest, not in the very final merger phase, but maybe in some immediate cycle just preceding merger where the orientation is very favorable?
Yeah, that's an interesting question. How much louder is it when it points towards you optimally versus quietest? I think that the SNR, the amplitude, is much more boosted by proximity than by orientation. So my guess is it's always going to be dominated by the final moments, even if it's pointing away. That's very likely.
In the interest of time, I think we need to move on. Let's thank you again.
Thank you.
So our next speaker is Jack Steiner. Jack received his PhD here at Harvard. He was a Hubble Fellow at the CFA, and now he's an Einstein Fellow over at MIT. And he's an expert at estimating the spin of stellar mass black holes.
Okay. Well, thanks very much for having me here. So as advertised, I'm going to be talking about a nicer look at stellar mass black holes. And for those of you who don't know what nicer and all caps is referring to, it's a new X-ray mission which is supposed to go up on the space station this past August. It has not gone up yet. We're very hopeful that it may go up in March, but this is a little bit contingent on SpaceX, which had an unfortunate incident in recent memory. And so once SpaceX has clear answers, we're hoping this will be coming soon. And the thing that I'm most excited about that NICER will do is inform our understanding greatly about stellar mass black holes. But to get there, I first want to show you where we are today. And this is the synoptic view of stellar mass black holes as provided to us by the titan of black hole instruments, the Rossi X-ray Timing Explorer, RXTE. So this is all told about a year of exposure time on stellar mass black holes, something pretty incredible and given to us by RXTE, which had a 16-year mission life. Now what you're seeing is X-ray hardness in the X-ray axis and detected flux in the vertical. So this is something like an HR diagram, but not distance corrected, for black hole behavior. This is some 30 stellar mass black holes that RXTE was able to monitor approximately daily as they went into different outburst cycles, or some of them always X-ray bright. And in the color, I'm showing you a proxy for timing noise, so some flicker variability that goes on in these black hole systems. And that flicker noise is something that NICER, which is an X-ray timing instrument, is going to tell us great details about. I'm not going to tell you too much more about that today, except for a couple of hints. But that's a whole, the timing domain is, there's a great wealth that will be mined there by NICER specifically. But just to give you a sense of what's going on in these accreting black hole systems, this is showing you an isolated black hole, GX339, that's gone through several outbursts as detected by RXTE. So in the right side of the diagram, so in red what you're seeing is the rising hard state. So what happens is when a new black hole goes into outburst, it starts off from quiescence, some very faint hard state. It rises X-ray hard, and then at some point it pivots, and it transitions to a soft state that's dominated by thermal emission from an accretion disk.
You may want to define hard and soft, because some people are not astronomers.
Yeah, sure. So,
What do you mean?
So by hard and soft simply refers to this is essentially a ratio of flux in a high energy band to flux in a low energy band. So something harder means it's peaked in high energy, something soft means it's peaked at lower energy roughly. And you'll see a little bit more what I mean about that coming up. But basically as the system goes through its outburst cycle, it starts off in a hard state, moves to soft, and comes back down, and there's a hysteresis. So you see that it doesn't transition back at the same intensity that it came through it. And very interesting phenomenology happens when it's going through these outbursting cycles. They produce jets, these ballistic bullets of jets that launch at a very particular region in their hardness intensity diagram. But all of this wealth of behavior is really something that tells us specifically about, we think, a fairly simple system with just a few elementary players. There's, of course, the black hole, but then around the black hole is a thermal accretion disk. And this is the source of the low energy, the cool X-ray photons. This is an accretion disk that's about 10 million degrees, emitting 1 keV X-ray photons. But then surrounding that optically thick accretion disk is some tenuous plasma that we call the corona. And the corona is very hot. It's about 100 keV characteristically. And we only detect it indirectly through its interaction with the thermal photons. And as you'll see in a moment, in its imprinting on the disk spectra. But we don't know too much about this corona, except that it seems to always be present. It scatters thermal photons into a power law component, a Compton power law, and then some of those photons return back to the disk after scattering, and the reprocessing of those Compton scattered photons produces what's called reflection component. For those of you who've heard
where it came from, this corona?
the corona, there are many ideas. Most of them are sort of tenuously related to magnetic fields. So magnetic processes that evaporate.
The sun has a corona. Every star has a corona. And usually it's magnetic field reconnection.
Yeah, so
Magnetic field, that's what makes it so hot? Why is it hotter than the
so it's why is it harder than the accretion disk? It's produced by, I guess, non-thermal events, but I don't know if there's a great understanding, except that it's something closer to it gives you something that's yeah, I guess I don't have a very good answer for that. But if you look at, for instance, solutions for ADAPs, these effective flows around black holes, some models for how you get a corona is that there's sort of a two-stage accretion flow, one of which is optically thick, gives you the disk, one of which is optically thin and gives you the corona. And there you expect the corona to be much, much hotter. So this is sort of a cartoon understanding. Empirically, we simply know that there is a corona that's present.
So the yellow cloud in your picture is the corona?
Yes.
It's a cloudy day.
That's right. So the typical spectrum for a thermal state of a black hole, so that when it's dominated by this bright accretion disk, looks something like this. So there's a prominent disk that produces maybe some 90% of the flux, and then there's this contribution from Compton power law. So this is the input from the corona right here. So really it's contributing in a way, so we can infer its presence, but again, it's largely mysterious. We don't quite understand what gives us the corona. And to show you how RXTE has looked at these black hole systems, This is showing you the RXT bandpass across this spectral domain, and you see that it's very sensitive to the thermal disk, and it's also sensitive to the Compton power law. But for those of us who are really interested in studying the details of what goes on in the accretion disk directly, and this is particularly pertinent for measuring things like black hole spin, you would really like to have something that's centered right around the disk, the domain of interest. And this is what NICER will do for us. So NICER is something completely sensitive to this disk component in a way that RXT simply was not. And just to show you a comparison of the two, this gives you a sense. NICER tells us a lot more about what's going on in the disk directly. For aficionados of X-ray astrophysics, I just want to put up a quick comparison to XMM, which a lot of people will be familiar with. NICER's effective area, that is its net sensitivity, is significantly greater than XMM. The one major difference is NICER will be a non-imaging instrument. It's simply a light bucket, so it'll count X-ray photons, but it will not provide images. That said, it's also going to be an incredibly sensitive timing instrument. It provides 2 orders of magnitude improvement over RXTE's timing capabilities. So we're going to be able to learn a lot about quick time domain science about these stellar mass black hole systems.
How big of an area in the sky is it counting from?
So its sort of peak effective area is about 1,600 square centimeters or thereabouts.
I'm talking about the angular size on the sky.
Sorry, I see. Yeah, so it's got about a 5 arc-minute field of view. That's compared to RXTE's, which was a degree for the collimator. Yes.
Could we see that last slide?
Sure.
So it's going down to, how far is it going down?
0.2 keV. So 0.2 to 12 keV is the nominal bandpass for NICER.
Well, the solid line was what again?
So the solid line here shows you the net spectrum of the black hole. So there's cutoff here at low energies, which is because whenever you're looking at a black hole system, you're looking through some interstellar gas, and that gas produces photoelectric absorption, which cuts off the lowest energy X-rays. So effectively, you're always limited to some degree at the lowest energy end by interstellar gas.
But the net spectrum is referring to what? That's measured, or is it theoretical, or is it?
So this is a spectral fit. So this is a model that includes absorption and the black line. Data are over here.
But I don't see any data, I don't see any data points over there.
That's right. This is an RXTE spectrum.
What is the line to the?
Right, the green line that goes off to the left there higher, that's the B2 type absorption?
Yes. That's right. And so green line shows you, the green shows you the net spectrum if there was no absorption. The red line is just the disk contribution if there was no absorption. And the black is sort of the full spectral fit when absorption is included as well.
So for each mass black hole?
So this is a 7 solar mass black hole. So the peak temperature, I should say, shifts around a little bit as you change the mass accretion rate or as you change the mass of the black hole, but it scales like those quantities to the 1/4 power. So it's a pretty slow function of changes in m dot or m.
And the corona component doesn't?
The corona component does change too with mass accretion rate, but more so with the state of the black hole. So there's more complex astrophysics in what goes on with the corona. But that's something we usually try to measure to, if we're interested in isolating the disk component, we sort of use model the corona and then sort of toss it away so that we can get at the disk physics that we're really interested in. I guess depending on your point of view.
And why is it plunging to 0.2 keV? It becomes so big there.
Yeah, so this is really, again, this is just the effect of the interstellar gas.
Okay, so I apologize if you're going to say this in advance, but this is for a 7 solar mass black hole. How much would that change for, say, like a 10 solar mass, a 20 solar mass, a 1 solar mass, and how many would you expect to see?
Yeah, so if you were to go up from, say, something like 10 solar masses to something about 100 solar masses, say, you would get something that's of order less than a factor of 2 change in temperature. So it's a sort of modest change in the peak in the spectral peak.
If you drop down to 1 solar mass, it wouldn't change that much either.
That's right, sort of similar. So the sort of tagline is the stellar mass black holes peak at 1 keV, and there's more change in the peak temperature as the system evolves through its outburst cycle, because m dot, the mass accretion rate, is changing. It starts low, gets high, and then it fades again. So that change is really sort of more impressive upon movement of the data than a change in mass would be. But mass does certainly set a degree of overall scaling.
So you would be able, with data from NICER, you would be able to say, oh, this is more likely a 5 solar mass black hole, this is a 20 solar mass black hole. Is that right?
So what I'll discuss in a moment, we'll sort of touch on that. I think it does have some constraining power on mass and spin together. So I'll touch on this in a couple of slides.
What's that the mass of the disk?
So the mass in the disk is very small. Dynamically, it's maybe 10 to the minus 10 times the.
The emission.
No. So it's the disk is optically thick. So you're really just probing a surface layer. If it was optically thin, perhaps there would be some dependence on the mass in the disk in that regime. But because this is optically thick, you're really just probing a surface, and it's dynamically negligible. It has no effect on the spectrum. So one last point about the sort of detector properties, again for the X-ray nerds in the crowd, is that a very important feature of NICER is that it has no pileup. So for people studying bright objects in our galaxy, stellar mass black holes or neutron stars, X-ray pileup is basically a kind of photon confusion that happens when 2 or more photons can be registered together and incorrectly sort of tagged as a single X-ray event. So this sort of confusion happens for detectors that have very long read times and register times. NICER will be clocking out something like 100 times faster than RxTE, which was the previous king of X-ray timing domain. And this is a very important feature of NICER, enabling us to do very detailed, precise studies of stellar mass black holes. And this is something that the current generation of X-ray detectors really can't do. And just to hammer home how NICER will be performing on the fly for us compared to RxTE, this is showing you the count rates versus that hardness, the same hardness intensity diagram I showed you a moment ago for GX339. For RxTE in blue, and now I'm showing you in red the count rate that we would expect from NICER. And you'll see that everywhere the count rate is essentially as much with NICER as it is with RxTE. But when the spectra are soft, that is, they're dominated by the accretion disk emission, you get something like a factor of 5 to 10 boost using NICER compared to what we got with RxTE. This is even taking into account the fact that NICER has smaller collecting area compared to RxTE. So this is really a feature of it having sensitivity in the right spectral domain to what's going on in the accretion disk component. Okay, so with that as sort of backdrop about the detector, I now want to really delve into what science questions are we going to be answering using NICER. And for me, as Michael mentioned, much of my work has been on measuring black hole spins. And just to review for you very quickly, the way in which we go about measuring spin using X-rays is basically to ascertain the radius of innermost stable circular orbit. So if we can measure this ISCO radius, then we're golden. We can infer black hole spin. So measuring the radius of the ISCO is the name of the game. And there are 2 methods by which this is presently being done. One is using thermal emission from the accretion disk and modeling essentially black body-like continuum spectra from stellar mass black holes. And as you go from non-spinning to rapidly rotating, what happens is the accretion disk moves much closer into the black hole. You get much hotter emission, much brighter emission for the rapidly spinning case. And similarly, if you were to change the black hole mass, this shifts around the temperature, this shifts around that peak. So essentially, you're measuring a size, and that size is always proportional to mass. So this is the case in which mass plays a role. You're measuring a combination of mass and spin to set this scale for the radius here. So the other method is using the properties of that reflection component that's induced by coronal Compton scattered emission re-irradiating the disk. And this gives you the so-called iron line profile. Here I'm showing you iron line emission, which comes at a rest frame energy of 6.4 keV. This is for a non-spinning black hole here, and this is for a very rapidly rotating black hole here. And what happens is, as you move the iron line emitting gas deeper into the potential well, you produce much more intensity in the low energy, the red wing of that iron line, simply due to the extreme gravitational redshift very close to the black hole. Okay, so in a nutshell, these are the two ways in which we measure our ISCO and get spin.
So you're assuming that the only reason the matter from the accretion just stops at that point is purely gravitational, as opposed to some possibility that it loses angular momentum some other way.
That's right.
So is that a big assumption, or is that something you can comment?
So I think that is an important assumption. We can empirically back that up to a significant degree. Now, we can't prove that there's emission that stops at the ISCO, but we can show for a few systems that over many repeated measurements, when the system is at very different luminosities, in one case we have 8 different X-ray emissions spanning about 30 years, repeated measurements, when the system is wildly different, you get the same radius to about 5%. So there's really no natural place to say that you're getting a constant radius except for the ISCO. But potentially,
there is another honest way to test your assumption, which is to see if you ever get a bigger than 1.
Yeah, this is true.
And allow for a bigger than 1.
And so in a number of cases, we have sort of done tricks to explore to see if anything is pushing past that boundary. So there's one system that is happy to push past a star of 1. That's Cygnus X1, but it's within error. So nothing is strongly demanding superspin. So this is a very good point. So nothing has really said our parameter space is not sufficient. Something seems funny. So Sig X1 is pushing on those bounds, but
that's an iron line, or
so this is a continuum fitting measurement. I don't think there's the same capability to test that for the iron line method. So I don't think we would be able to make a strong claim in the case.
I guess also if you see that the ISCO is further out than A equals 0, allowed given your estimate for mass, that would also apply.
This is true. So there are some, if you have a retrograde spin, then that pushes you outside. So you can go out to
9M is the largest it can be.
And there have been some tentative claims of retrograde black hole spins, but nothing convincing yet.
That was my question.
Oh, okay. Perfect. Yeah, so these are the two of the real games in town for measuring black hole spin. And NICER will do a better job at both of these techniques than our current fleet of X-ray instruments, with the possible exception of NuSTAR for the iron line method.
One other aspect that you didn't mention, you assume that the orbital plane is in the middle of the spin axis.
That's right. So we
and how dynamically the star is feeding it an angle. Can you comment on why?
Yeah, sure. So the time scale over which you expect an accretion disk that's initially tipped to come into alignment with a spinning black hole is of order 10 to the 7 years, a few times in the 7 years. So something we think is relatively quick. And actually, it doesn't come into alignment. The black hole gets tipped into alignment. The angular momentum reservoir for the binary star system is huge. So there's a little bit of uncertainty there, and sort of searching for misaligned disks is sort of it's a little cottage industry right now, but there's no concrete evidence for it. One particular system, we were able to use the motion of its jets, assuming they were launched along the spin axis, to test against the binary inclination angle, and we're able to say it doesn't want more than it's aligned to within 10 degrees is sort of the extent to which we've been able to test that, but there is this possibility too, yes. Okay, so in addition to those two techniques, which I would say are calibrated and established for measuring black hole spin, there's an important and exciting frontier approach which takes advantage of the time domain. So this is spectral timing now at sort of kilohertz frequencies for stellar mass black holes. Importantly, the kilohertz domain is the Keplerian frequency at the ISCO. So this is why kilohertz QPOs start to look interesting. Now what's really neat is that there are a handful of systems, I believe there are now 7, that have high frequency QPOs at a 3:2 frequency ratio. And this special 3:2 ratio that you're seeing here for peaks in the power density spectra is sort of calling theorists' attention, saying there's some fundamental harmonic going on. This is, these are special frequencies. They seem to be stable for a given source also. So repeated observations at different luminosities sometimes show these QPOs. However, they're very difficult to detect, and they're very intermittent. So we only have a handful of systems that have these high frequency QPOs, and now there are 5 of them that also have spin measurements. So you might say, okay, well great. You must have the model that tells us how these frequencies relate to spin. I wish I could tell you, yes, we've solved that. Right now, there are many, many models for how you produce these via Keplerian frequencies, epicycles, different seismic modes, corrugation modes in the accretion disk, and none of them really seem compelling or convincing, and there's great uncertainty now about what is the right model. And the only way in which we're going to resolve this is with better timing data on more black hole systems. And NICER, being a new X-ray detector that is more sensitive to the accretion disk than anything that's flown before it, we hope will give us that. And so we're hoping NICER will become a factory for these high-frequency QPO measurements, and we'll be able to measure spin using the previous 2 methods, continuum fitting and iron line, and also learn something about this high-frequency QPO model. By the way, this promises to be the most sensitive measurement to both mass and spin. So if we can get the right model from this will really be a game changer for people who need precision data, for instance, to search for gravitational waves. I'm gonna, I think, skip ahead a little bit, except to tell you one other piece of very nice astrophysics that we're going to probe using NICER, and this is the so-called slim disk model of accreting black holes. So the continuum fitting method that I discussed before relies upon this sort of thin disk limit for what you expect from the spectrum of a stellar mass black hole. So that is, we restrictively use that method when the luminosity is relatively low, so the accretion disk is not puffed up to some very bad extent by its own radiation pressure. So only when radiation pressure is low do we apply that thin disk model. But we have a lot of data where it's very bright, close to its Eddington limit, and the disk, it gets very fat and thick. So with NICER, we'll have such sensitivity around the peak of that disk that we think we'll be able to start probing the structure of the accretion disk to an unprecedented degree. This is showing you a data set for a particular black hole system near its Eddington limit, where I've put in a slim disk model, that is when the accretion disk is fat, and I've fitted it with a thin disk model, where it assumes that it's razor thin. So for RXTE in black, there's essentially no difference. I'm able to obtain a good fit using the wrong model. With NICER in red, I can tell immediately that the thin disk model is no good. So we'll be able to empirically calibrate these slim disk models, and in turn that will feed into detailed simulations of black hole accretion. Folks like Oleg, who you heard about a couple weeks ago, are working on these sorts of models. So I think we'll be able to learn a lot more about accretion at the high luminosity end as well. And one last exciting prospect for studying these stellar mass black holes is to look at some strange accretion instabilities that we see going off in black hole systems. There's one particular titan in the realm of stellar mass black holes, GRS 1915, that has famously a library of unusual modes. This is showing you something called the heartbeat pattern, which repeats roughly every 100 seconds a pulsation by a factor of about 5 to 10. Pulsation by about a factor of 5 to 10. And
Do you see those with neutron stars too?
you see different kinds of pulsations from neutron stars. This sort of instability is really is quite unusual. There are only 2 black holes that we've seen this sort of pattern appear in, and it's only for certain times. Neutron stars show very sort of sharp bursts, type 1 and type 2 bursts that are classified, but it's something very distinct from this. So these sort of unusual modes are things that we've been able to see in time domain, but we haven't really been able to probe in detail. And this is showing you just a few more of these types of light curves. So this is over time, these strange oscillations that repeat over time scales of 30 minutes or so. With NICER, we're going to be able to probe, we're going to be able to obtain spectra of each of these cycles at the sort of 1 to 0.1 second time scale, which is critical because that's the viscous time scale near the ISCO. So we're going to be able to learn something detailed about the astrophysics of what's going on to generate these sort of instabilities, whether it's a thermal viscous process or something else. So with that, I think I've eaten up my time. I'll put up these sort of laundry list of questions we think we're going to address with NICER and take a question or two. Thank you.
One quick question.
Can you discuss the timescale of this hysteresis? And also, I was curious that these periodic heartbeat modes, what part of that soft hard flux
Yeah. So each of these, so GRS 1915 has some about 24 of these different instability modes. Each of them takes place in a different realm of hardness intensity. This is up top is a hardness diagram for each of these, where there are 2 different spectral bands essentially. That's a ratio again of some high energy flux to some low energy flux. So each of these takes place in sort of a different spectral domain and swings around in different oscillations between them. So I can't give you a single answer for how that behavior goes, but it's a time scale of some 100 to 1,000 seconds would be characteristic for all of these.
Across the hard stuff.
So for each of these, yeah. Oh, the full outburst cycle. So black hole transient, when it goes into outburst, takes about a year, a few months to a year, and that hysteresis you see that gap occurs, after a time scale of a few months. Yeah. Sorry.
Oh no, I think that's 2 questions.
Okay.
Okay, I think we gotta move on. Let's thank Jack again. So our last speaker today is Dheeraj Pasham, or DJ, I guess, and he got his PhD from the University of Maryland, studying ultraluminous X-ray sources, and he's now an Einstein Fellow at MIT, also studying tidal disruptions and also intermediate mass black holes. And today he'll tell us about optical to X-ray echoes, calling it tidal disruption.
Thanks, Mike. So I'll try to be quick. I'll try to finish my talk in 20 minutes. So my name is DJ. For those who cannot pronounce it, just call me Dheeraj Pasham. But I just started a postdoc at MIT, and today I'll talk about multi-wavelength timing study of the recent tidal disruption flare. James, who's here, who's been a part of this project. So this is just a brief introduction. What is a tidal disruption flare? You have a supermassive black hole, you have a star coming in close to the supermassive black hole, and if the tidal forces from the star exceed its self-gravity, it will be disrupted to cause a tidal disruption flare. And this is really fascinating because these events can, in principle, shine across the entire electromagnetic spectrum. So people from optical, radio, X-ray, can study this condition. So aside from them being really spectacular phenomenon, they can also tell us something more about hidden black holes that you would never see otherwise if they were not tidally disrupting a star. They can tell us about spins of these hidden black holes, masses of these black holes. They can also tell us how jets can be launched from these black holes.
How close to that? That sounds like
within few parts of radius. This mass of these. the few short period. So the second point is they can tell us about how an accretion disk forms around a supermassive black hole in real time. And this is what I'll talk about today. The focus will be on the disk formation around these supermassive black holes.
Isn't the star much physically bigger than a few short radians?
Yeah, no, it's not a few. It depends on the mass, but for Sagittarius A star, it's 100 short. It's 10.
There's 6 mass.
And above 10 to the 8 solar masses, the black hole swallows the star whole.
So there's a range in the black hole masses from 10 to 4.
So for a star like the sun, and the black hole at the center of the Milky Way, the mass ratio is roughly a few million. Okay, so you take the cube root of that, it tells you how many stellar radii. So it's about 10 Schwarzschild radii for the sun and Sagittarius A star. And then if you go to 10 to the 8 solar masses, then it swallows the star core. So somewhere between 10 to 1 Schwarzschild radii is where the disruption is.
Is there hope we could see one of these? The star?
Oh, we've seen that.
Yeah.
Oh, Sagittarius? No, it's once every 10 to 5 years.
We might have seen one, a
100,000.
historical one from Sagittarius A star, possibly.
Yeah, the dinosaurs. So.
So anyhow, one of the open yeah, probably have to Some of the open questions in the field of TDEs is how does the material circularize after it gets disrupted? How does the material from the star get into a disk? That's one of the questions. And then the other question is, if it does form a disk, what kind of a disk does it form? Does it form a thin disk or does it form a thick disk? So these are the questions that are still to be answered. And I think the answer to these questions really tied to the origin of the optical and UV emission. We still don't know where the optical and the UV light is coming from these events. These are the three possible scenarios from which you can have the optical and UV emission. One, you can have the optical and UV from simply the disk as a thermal black body, or you can have the tidal stream interacting with itself, and at the interaction site, you can produce optical and UV. Or you can have simply the X-rays coming from really close to the black hole, just reprocessing in the ambient medium and producing the optical. So by the end of this talk, I'll tell you at least from this source where the optical and UV is coming from. So the source I'll be talking about today is Assassin 1411. And it's really been a poster child for tidal disruption flares because it's shown all the classical predictive properties of tidal disruption flares. It's shown outflows early on, it's shown radio emission, just coincident with the X-ray flare. And it's really amazing because it shined across the entire electromagnetic spectrum, X-rays, UV, optical, and radio. The true multi-wave of TDE. I'll just talk about what we did first, and then I'll talk about what the results can tell us about the system. The first thing I did was simply extract the light curves all the way from X-ray light curve, UV light curve, and then optical light curves. These are the same flare observed in different optical bands and X-ray band. So my expertise is in timing. So what I did was naturally cross-correlated all the optical and UV light curves with the X-ray light curve. Why, you might ask? We know that the X-ray emission is coming from very close to the black hole. So if you want to understand where the optical and UV is coming from, then you want to see if there is any dependence of the optical UV fluctuations with respect to the X-rays that are really coming from close to the black hole. So if we know, if we establish that there is some sort of dependence on the optical UV fluctuations with respect to X-rays, then we can map out, where it's coming from. So this is simply a procedure I'm describing here in terms of cross-correlation analysis. We have the X-ray light curve here, and an example UV light curve on the right. The first step is to simply detrend the data, remove that long-term trend. The red is showing the long-term trend. You just subtract the data minus that trend. Same thing here, you have the data minus the trend, and whatever is left over you cross-correlate and see if you see anything. Shown here is the cross-correlation function of the two light curves that I showed earlier. And what this is showing you is that the cross-correlation peaks at about 30 days, and a positive lag implies that the X-rays are lagging behind the optical/UV light curve that you're cross-correlating it with. there's just a 95% confidence contour and a 99% confidence contour. So the takeaway point from this slide is that the X-ray fluctuations lag behind the UV fluctuations.
Just go back one slide.
Yeah.
The real data. So is it all coming from the signal?
It's the next slide. So anyhow, these are the rest of the CCFs. X-ray versus UVW2, UVM2, U, G, B, and everything. Now the obvious question is you want to go back to the light curves and convince yourself that it's real. So shown here is the lag corrected UV. So basically they've shifted the UV by 30 days. And then shown here is the X-ray interpolated at the same values as the UV. And the red curve is the running average of the X-ray data points, and the blue is the running average of the UV data points. So the lag is coming from basically these features. And then 1.5. And then there's more. There's the other guess.
Because the data is not taken evenly spaced time, so we have the problem of the cross correlate. What do? You extrapolate or you?
Yeah, so the way it's done is you have data from light curve 1, light curve 2, you move light curve 1 by, say, certain delta lag, you interpolate at the same values as the light curve 2, and then do a cross correlation, and then shift it again, interpolate, do the cross correlation, and just build up all the way from whatever range of lags.
Yeah, interpolation introduces some noise.
Well, there's also another method you can do this. It's called the discrete cross correlation function, which does not involve any sort of interpolation. And to show in the paper, we show that it's independent of the interpolation. So we do that.
So in the first X-ray light curve, you showed the points had error bars. When you detrend that light curve, you have some, if you go back, yeah. So when you detrend this, you basically have no significant features in the X-ray, right? You just have a flat curve that would be consistent with these data.
Not really.
No?
I mean, feature over there, the error bars, not that much. The error bars, not that much.
So that feature, the one really the feature by which you cross correlate, that is significant?
Yeah, it is significant. You can see the error bar is that much. The error bar over here is that much. And there's 2 sigma error bars for 90%.
Okay.
I mean, I guess it is possible that, say, the UV feature there is not related to that. Right.
Yeah, so the point is, what is the possibility that the same feature appears in UV 1900, 2200, 2600, 3400, and so on? So that's the whole point I'm trying to make. But you also see the same features in, say, the U band or B band. So the idea is it's not just one band that the result is dependent on. So you want to make sure if it's just.
But that's a noise effect you're worrying about there. If there were, some broad spectral dependence to this stuff, and you have a UV bump that goes across all of UV. You could assume that that was totally independent of the X-ray emission, and now you just cross correlate with your lag. You have multiple bumps or different shapes of movement.
Yeah.
So it's a little bit of work.
Having more bumps and blips would be ideal. But what's interesting is there's another source that went out as well, and even that source shows similar lags. So I've convinced myself that okay, it's not just one source that's doing that. So there's another source.
Sounds good.
So it's okay. So yeah, should definitely point it out. So an obvious question is this cross correlation driven by the X-ray light curve? So the one way to rule out is simply get the autocorrelation function, which is cross correlating the X-ray data with itself, and to see if there's any lag features in there. In the feature that in the time lag range of a few tens of days, there's no significant features there in the X-ray autocorrelation function telling us that it's not coming from just the X-ray light curve. It's from the transfer function between these two light curves. So like I was saying, you can ask each peak was it significant about 95-99%, which is not significant itself. So you can try to estimate some sort of global significance. You see you divide the entire optical UV into small filters, UV1, 1900, 2400, 2600, and you see it in all of them, and you can estimate the global significance in a sense, and that's statistically significant. So this is just the X-ray lag versus frequency. They're more or less at the same value. The error bars are huge, right? So the takeaway point is that the optical and UV fluctuations appear to lead the X-ray emission by about 20 to 40 days. We are in the process of submitting the paper. So what can we conclude based on this result? Remember the slide I showed you earlier on about these questions? I'll try to address these questions based on the result. So the first obvious thing we can do is we can rule out that the optical and UV emission is not dominated by pure X-ray processing. It's because if it were X-ray processing, you would have first X-rays, then optical UV. Here it's the other way around. And the second thing we can rule out is the X-rays are not produced from pure thermal seed photons from the inner disk. If that were the case, so you can have the inner disk producing UV and optical that can constantly scatter, get energized in this corona that Jack was talking about, and then produce X-rays. If that were to be the case, you would expect the optical and UV to lead the X-rays. However, the time scales that you expect from this process, the time leads, for a black hole that is 10 to the 6 to 27, which is likely the case for this scenario, this system, is only in the order of a day or 2 days, depending on how you push it. But if the black hole is bigger, if it's too big, then like I was saying, the star would just get smaller and you would never expect to see the TD. That was something. So the most important thing, most important conclusion we can get out of this result is that if you have a standard thin disk, which is a disk that is optically thick and then geometrically thin, it's just a razor sharp thin disk around a black hole, you can work out what the viscous time scale in the disk should be as a function of wavelength. Shown here are curves for different black hole masses, different accretion rate, and different viscosity parameter of the disk. And these are the data points down here. So what this is telling us is for any reasonable set of black hole mass, accretion rate, alpha viscosity, you cannot explain these data points with propagation of just fluctuations in the mass accretion rate traveling from the outer disk inwards with a standard thin disk. However, if you make the disk very elliptical, you can make this work because in an elliptical disk, the viscous time scales for fluctuations to propagate inward is very fast. So based on this, we proposed two models for this scenario. One is the shock setup center model, which is you have the black hole, you have the debris stream from the star that's disrupted, interacting with itself, producing the optical UV emission at the shock site. And then as it falls inwards, it produces X-rays eventually on a time scale comparable to free fall time scale from the interaction site. Naturally explaining the UV optical bumps first and then the X-ray later on. The second model is simply having a very elliptical disk, in which case any mass accretion rate fluctuations from the outer disk will just travel inwards at a local viscous time scale. And for an elliptical disk, the viscous time scales are very short, comparable to the free fall time scale.
DJ? Yeah. Have you considered how jets might do this?
Jets might do.
If you could get optical emission, say from from a jet and then have it crashing into the ISM to give you X-rays. I mean, I don't know if this has been looked at in the context of jet emission.
So the optical would come from synchrotron tailing, or is it from synchrotron?
Yeah.
So John Miller did fit the X-ray spectrum alone and found that it was pretty consistent with the disk-like model. So didn't really it's not a very hard X-ray spectrum. It's not really any evidence of a jet.
And your takeaway point is that in this particular poster child PD, the optical UV emission leads the X-ray emission by 30 days after. And the most important conclusion based on this result is that this is telling us that it's the event, whatever event we saw, is not a typical AGN outburst. Because if it were an AGN outburst, the disk should have been more like a thin disk, which is consistent with the data. Well, thank you.
One or two quick questions for teachers.
So clear.
So, Dheeraj, do we have this kind of data for other PD candidates? So we have X-ray, we do have X-ray UV optical for the other side.
There's optical UV for some of them. X-ray, not so many. Actually, not any.
Swift 1624.
There's no optical and UV is completely ignored. Those galaxies is very good.
Okay, well, let's thank all our speakers again.
What is it?